Hello and welcome to another SAE Expert Insight. My name is Sebastian Blanco. I'm the editor-in-chief of SAE Automotive Engineering Magazine, and I'm here today with Mark Hermeling, Head of Technical Marketing for Adacore. Mark, how's it going today?
Fantastic. Thanks for inviting me, Sebastian.
Of course, and in order to let everyone know why we invited you, can you tell us a little bit about yourself?
Yeah, absolutely. So my name is Mark Hermeling, as you said. I'm the head of technical marketing at Adacore, and I help explain how our solutions benefit our customers. We help solutions around development tools, tool chains, specifically for high integrity software systems. So think automotive, aerospace, defense, medical, industrial, those type of things.
Okay, and on that point, it's true that most automotive teams have decades of C and C++ investment and a MIZRA process already in place. I've heard you argue that a language subset is a discipline and not a guarantee. For an engineer who's being asked to justify a switch to Ada Spark or Rust to their functional safety league, what does the risk reduction look like in concrete terms? And how do you weigh that against the retraining and requalification costs?
Yeah, that's a fantastic question, and just to kind of back up that statement a little bit, many people have been building software in C and C++ for decades, right? Those languages have really served us well, but we also know that those are very powerful and at the same time very dangerous languages, right? With C and C++, they give you the power to do anything you want in the memory space, which very often is what we needed to get the most out of slow processors and small memory spaces and those type of things. But there's been a tremendous shift in the market where people are demanding more memory safe programming languages to avoid a whole bunch of the problems, right? If you start searching on like what are the security problems that most of these systems run into, it's typically related to memory safety, right? So things such as buffer overrun, null pointer dereferences, array out of bounds, those type of things. And those can really easily happen with C and C++. So MIZRA, all of the MIZRA standards, you can really see that as a language subset, right? If you stick to the MIZRA C or MIZRA C++ language subset, you avoid those type of problems. Now, the challenge with that is, as a software developer, you're trying to build the best software you can, right? So you have a set of requirements that you try to implement most elegantly in a way that those requirements can evolve, right? And you can serve today's problem and also next week's problem and next year's problem. But then on top of that, on top of actually solving that requirement, delivering on that requirement, you have to adhere to this MIZRA C and C++ subset to keep the language safe, right? To make that problem that you have solved, the code that you have developed, safe
Mhm.
and secure. The challenge with that is that none of those MIZRA C and C++ evaluation tools that exist in the market are 100%, right? So you have static analysis tools, you have compilers, you have test tools, you have code coverage, but none of these can actually guarantee you that your code is 100% MIZRA C++ requirement implemented, right? Validated.
Yeah.
Because a lot of the MIZRA rules are just non-decidable, right? If you say that there shall not be any buffer overruns in the source code, there's no way to prove in C and C++, no realistic way right now at least, to
Mhm.
prove that you don't have that buffer overrun out there. So those languages are powerful and dangerous. And in the drive to memory safety, there's two different languages that are popping up in the industry right now. Rust being one of them, right? Many people talk about Rust. It's very popular. Google is working with it. There's a fantastic presentation by Toyota on Rust usage in the non-safety related code of a Toyota RAV4 of the latest models. Fantastic. The other language that's really popular here is Ada Spark. And Ada Spark is a language in which you can write software in a very easy to understand syntax. And number two, you can prove the absence of runtime errors through formal methods. So now you don't have
Mm.
to contend with MIZRA anymore. You don't have to deal with extra tools to prove that there's no more memory issues. The language subset of Spark can prove to you through formal methods and a mathematical tool called GNAT prove that there's no more memory error. So now it's an exhaustive proof that there's no more path through the source code that can have a buffer overrun, that can have um, a null pointer dereference. And you can do that during compile time. So before you run the code. So think of that as a step, right? As a software developer, you have this requirement that you have to implement. And as you implement it into the language helps you during the programming to avoid making those programming mistakes, as
Mhm.
opposed to the MIZRA side where you first solve the requirement and then you have to go prove those MIZRA violations are no longer there.
Mhm.
So it's a really neat way of solving that problem. It helps the engineers, there's much less friction from the engineering team. And for the quality team, there's much greater trust in the final implementation. So yes, there is some retraining. There is
Mhm.
some different approach costs, right? There's a learning cost to switch to those type of languages, and nobody will switch everything overnight. But as you think of implementing new pieces of your software stack, looking at those memory safe languages, I think, is the best thing to do right now.
Mhm. On the topic of finding problems with the code, you haven't mentioned AI specifically, but I think we're going to get into that here because LLMs can now find defects working from compiled binaries, not just source, and that most of what they surface traces back to undefined behaviors. From an engineering standpoint, does that change how teams should think about their attack surface and verification strategy, or is it more a matter of reframing risks that were always kind of there in the code?
So I think they should absolutely rethink how they build these systems, right? And by the way, that quote came from one of our customers that actually had a piece of safety certified code that they reevaluated with AI, and they found a significant amount of security defects in it. And
Hmm.
the important part to realize here is LLMs are really good at finding uncovered problems in source code, typically having to do with undefined behavior. But number two, they're really good at then finding paths through the source code to trigger that behavior. So that means you
Hmm.
don't just have a defect, you have an exploit to go with that defect as well. The moment that you have an exploit against undefined behavior, your safety argument is out the window, right? There's no
Hmm.
more safety if you don't have security because there's other, you can have the code misbehave, there's other paths through the source code that are all of a sudden possible. So So the fact that this is possible right now should make everybody pause and say, is what we're doing right now really still good enough to deliver high levels of functional safety with these languages where we know that we haven't caught all the problems, right? Because that's what we just talked about with MIZRA C and the MIZRA C++. You can do a lot of effort, but the LLMs prove that there's still problems in that source code while evaluating source code or binaries. The
Hmm.
second layer on top of that is you can kind of say, okay, I'll just test my source code with an LLM, right? Well, today's LLM you can test it with. Next week's LLM is going to be even better. So next week's large language model may uncover things that this week's model hasn't uncovered yet, right? So you're on this rapid um, treadmill trying to catch up, where taking a step back and saying, should I just switch to a programming methodology that avoids these problems altogether? What is the benefit that gives me as a peace of mind, as a engineer satisfaction perspective as well, right? They now can really focus on delivering the code that they want, as opposed to trying to race after these latent defects.
Hmm. And wrapping up here, this idea of like people working sort of with the new, AI versions of code and the ways that we can, have these other tools that help us work with our tools that we already have. There are all sorts of ways to do human in the loop, um, you know, quality tests at the end. Formal methods can give a verification check that's independent of who or what wrote the code in the first place. And what matters, which can matter as agents, these AI agents start generating specs, tests, and implementations. What does keeping a human meaningful in the review loop actually require? And where does formal verification genuinely reduce the reviewer's burden versus just shifting it?
Yeah, this is the big question of our times right now, right? Because LLMs are really good at generating code. The agentic artificial intelligence platforms over the past 6 to 9 months have evolved so far.
Mhm.
It's really unbelievable and very exciting. However, we work in a high integrity software field, right? We have functional safety requirements. So we want to make sure that the code is properly tested and properly reviewed before shifting it. So if you have an AI generate code for you, and then that AI generates, I don't know, 3, 4,000 lines of code that is supposed to go into a safety application, having humans review that code constantly, it's not scalable, right? You cannot have an engineer sit 6 hours a day or 4 hours a day and just review code. Like the mental process doesn't work that way, right? It's no longer reliable. So the crux of the matter is what you need is you need to figure out a way of how to go from requirements to code, to test, to code coverage through the entire functional safety process without having humans just there to review, right? You need a deterministic way of harnessing the power of these artificial intelligence systems. And if you think about it, like a human is also a non-deterministic system, right? A human generating code versus an AI generating code, they're both liable to make mistakes, right? So what we now need to come up with, and Adacore, of course, is working really hard on this, is how can I get some form of deterministic trust to go from my requirements to the actual system that runs? And our argument is that with languages with formal methods built in, if you have at the beginning of your code the requirement of what that software is supposed to do, you can have two things. Number one, at the very least, you can prove there's no more undefined behavior, right? That's one part of the functionality of formal methods. The second part of that functionality of formal methods, you can actually prove that the code does what it's supposed to do. So if you write your requirements in your source code, let's say a binary search, right? Let's say I need to program a binary search. I, of course, want to make sure that there's no more crashes and buffer overruns and array out of bounds during my binary search. But it's really easy to write a spec for what a binary search does. And the formal methods can then prove that the implementation that is there, whether that was AI or human generated, actually matches that specification. So as opposed to reviewing every single line of source code, the engineer can now look at requirements and specification and start matching that, start creating traceability with that, and then walking that through a functional safety process. So I get a lot of questions and people saying, hey, would you trust a car that has code that was AI generated in it? And I would say absolutely. If it has gone through a full functional safety quality process, then absolutely. But that process needs to be well done. And Adacore, with our formal methods, is one of the companies that can help there.
Mm-hmm. Well, Mark, that's a great place to leave it. A lot of big questions, a lot of good answers. Thank you so much for joining us today and here on SAE Expert Insight.
Yeah, absolutely. Thanks for inviting me.